Alrighty, so now we get to see what happens when we take the chain rule, which is a pretty useful and powerful shortcut, and we combine it with all the other shortcuts that we've talked about, like product rule, quotient rule. So really it comes down to the identification of what is the function doing, what is the main operation of the function. And sometimes it's easy to tell, sometimes it's not, right? So when I look, for example, when I look at letter C, excuse me, it's pretty easy to tell that this function h is at the very big at the very base level here. We're dividing, right? We're dividing e to the 4x divided by sine of 2x. I can see the division line. I know that I have to use the quotient rule. And if I'm going to use the quotient rule, then I have to set up my quotient rule in the correct manner. So I'm going to set up the quotient rule, and my quotient rule says take the derivative of the numerator, the top, times the denominator, the bottom, minus take the derivative of the bottom, the denominator, times the top, and divide everything by the denominator squared. And I'm going to put, I call it the hovering the hovering square. I'm gonna put it there in between the sine and the 2x, meaning that we're squaring the whole denominator. Okay, so this is what I need to do. To finish this derivative, I've set up the quotient rule. I just need to find this prime and this prime. But both of those primes involve a chain rule. They involve a chain rule because I have an outer function and an inner function. I have an outer function and an inner function. So that's going to require me to do the chain rule. When I do the chain rule, the derivative of e to the 4x. Well, the derivative of e to the 4x is the derivative of the outer function, which is just itself, times the derivative of the inner function, the derivative of 4x, which is just 4. And then don't forget, we still have sine 2x there. And maybe I should write them a little bit closer. Sine 2x minus, I'm supposed to take the derivative of sine 2x, the derivative of the outer function, with the inner function still in there, times the derivative of the inner function, which is 2, times the e to the 4x that was already there, all divided by sine squared 2x, or sine 2x quantity, the whole thing squared. All right. Can I fix this? Can I make it nicer? What can I do? I don't know if I can, other than maybe we can factor out a 2. Maybe we can factor out an e to the 4x. That's going to leave us with 2 sine 2x minus cosine 2x all over sine squared 2x. I guess I can do that. That's one thing I could do. I think that's where I would leave it. But I have found all my primes, I found all my derivatives, and I'm done with example C here. The big idea is we are now applying multiple rules, not the chain rule multiple times, but multiple rules like the chain rule twice and the quotient rule as the main setup for our derivative function finding. If I go back to A or B, and I made my printout disappear. If I go back to A and B, I think I'd rather do B. So when I read it out loud, I'll read it as g of x equals x squared times the square root of 4x minus 1. So there's a clue that I have to do the product rule. Now, I will note I have a square root. So what do we do with square roots? We always rewrite them as 1/2 powers. Great. So now we're going to do the derivative of this. Derivative of this function is the derivative of the first function times the second function, exactly the way you see it, plus the derivative of the second function times the first function as you see it. This is the layout. I call it the blueprint. Here's the blueprint of the product rule. For the first prime, for the first derivative I need to take, that's just a power function. So we can do the power rule. The power rule would be 2x, and we're done. By the way, if this was a 1/2 power, remember that's just square root of 4x minus 1. Plus, the derivative over here is going to be 1/2 with the inside still in it to the negative 1/2 times the derivative of the inside, and the derivative of the inside is 4, times the x squared that was already there. So I did a power rule with the outer function. Something to the 1/2 is 1/2 times something to the negative 1/2 times the derivative of the something, the derivative of the inside, which is 4, and then times the first function that was already there. Okay, so now this is what I have. Plus 1/2 of 4, that would be 2x squared. Oh, but I have a negative exponent. And negative exponents tell me to take a reciprocal. So then this is really 4x minus 1 to the positive 1/2, which is just the square root of 4x minus 1. This could be my answer. Some multiple choice options might want us to combine these fractions and get a common denominator and then go from there. But this is my derivative. So if I asked you to find the slope of the tangent line for g of x at x equals 1, well, now I have my formula that if I substitute 1 wherever I see an x, I can find the slope of that tangent line. We can do one more. I'm not sure if we want to do A or D. I think we should do D. I think A is a little bit more straightforward than D. So maybe we should do letter D, and then that'll be the end of the section where we're just practicing the chain rule in conjunction with other rules and in cases where we have to do multiple chain rules. All right, first thing to ask yourself, what's going on? And if I read it out loud, I'll read it as k of x equals 3x minus 1 quantity to the third power divided by 2x plus 5 quantity to the fourth power. Well, I'm dividing. I got to use the quotient rule. So the quotient rule says take the derivative of the numerator, the top. I'm going to put a prime. I haven't taken the derivative. I'm going to take the derivative. Times the denominator, the bottom, minus, we have to take the derivative of the bottom. Let's make sure that prime kind of stands out, times the top, the numerator, all over the bottom squared, but the bottom is already to the fourth power, so I'm going to have to square that. Well, what happens when you square something that's taken to the fourth power? What do you do with the exponents? If you say you multiply them, you are correct. All right, let's find the derivative here. Oh, look, there's an inside and an outside. So I'm going to take the derivative of the outside. The derivative of the outside is, and let me use 3 something squared, but with the inside still in it, times the derivative of the inside, which would be 3. So the 3 something squared came from the something cubed, with the something still in there, times the derivative of the something, which is 3. Keep going, times 2 plus 5 to the fourth, minus. This is where keeping things flowing and kind of having a neat workflow showing is going to make your life a lot easier. Let's take the derivative of this. I have an inner function. So take the derivative of the outside. 4 something to the third. And my something is 2x plus 5. But then I have to multiply by the derivative of the something, which is 2. And then multiply by the top part, which is 3x minus 1 to the third. Whoa, that's a lot of stuff going on here, right? Okay. Can I simplify it? I'll try. In a free response part, there's no need to simplify. If I had asked you to find the derivative at 2, just plug in 2 now, right? I can plug in 2 wherever I see an x and figure that out. You don't need to simplify before you substitute. But if it's a multiple choice, then that might have to. Let's see. Well, I notice that this has 3x minus 1 squared, so there are two 3x minus 1s. This has 3x minus 1 cubed, there's 3. So at the most, I can take out 2. I notice this has 2x plus 5, 4 of them. I have 2x plus 5, 3 of them. So at the most, I can factor out 2x plus 5 cubed. So then what's left? Well, the 3 and the 3, that would give me 9. The 3x minus 1s, I've already factored out. The 2x plus 5s, I guess there's a 2x plus 5 left. Right? The key here is when I multiply these outer times this, then it should give me back to where I started. Minus. 4 times 2, that would be 8. I already took all of the 2x plus 5s out, and I took all but one of the 3x minus 1, so there's a 3x minus 1 left there. All of it divided by 2x plus 5 to the 8th. Holy cannoli, that's a lot of algebra. Well, these three 2x plus 5s can reduce with 3 of these 8 2x plus 5s. So I'm going to say this is 3x minus 1 squared. These guys are going to be gone, and I'm going to have 5 left over on the bottom. Is that right? If I take 3 of the 8 2x plus 5s and cancel and reduce them out, then I'm left with 5 of them there. And inside these brackets, I'm left with 18x plus 45 minus 24x plus 8. And so if I have to simplify, which I would not recommend doing, I think minus 8 minus 1, that is plus 8, this is 45. So together that's 53 minus 6x all over 2x plus 5 to the 5th. This would be my derivative. And man, what a workout, mental workout that was. What were we trying to do? I forgot. Oh, we were trying to apply the chain rule with other rules like the quotient rule, the product rule, or multiple chain rules. And in letter D, we definitely had to set up a quotient rule. And when we found the derivative of the top, we had to use a chain rule. When we found the derivative of the bottom, we had to use a chain rule. And really, I guess I need you to understand this is the derivative. Everything else that followed is just me trying to simplify it. But as I spend more time simplifying, the clock is ticking and I'm losing minutes. So I shouldn't do that. But I guess if it was, I don't think they'd give you a multiple choice question like this. But if they did, then maybe I do need to simplify and then find which choice marks is the one that best describes this derivative. The moral of this part of 3.1 is the chain rule is not going away. The chain rule is going to help us do something called implicit differentiation next week. And we need to practice to get into that flow of whenever we have an inside function and an outside function, we take the derivative of the outside with the inside still in it times the derivative of the inside. That's the big idea for this week.